occasion to have at De La Pietra lectures. I mean, we are grateful to the De La Pietra families. Well, the university, they are very generous with the university, and they're also extremely generous with the Simon Center. And in fact, they allow us to bring luminaries like Avi and others to illustrate and to educate us and to have some fun with plenty of discussions. Now, you've come to listen to him and not to me, but I should simply say that, Avi is a Harvard Math professor at the Institute for Advanced Study in Princeton, in the School of Mathematics. He's a world expert in complexity theory, cryptography, graph theory, and he has been distinguished with or laureated with some of the most important prizes. Among the last ones was the Turing Award. He's also gotten the Abel Prize in mathematics. He had the Levalina Prize, the Gödel Prize, one of his former colleagues in Princeton. So anyway, if you go to his webpage or to even the Wikipedia page, the number of awards is just an incredibly long list, which of course is all merited. Now he's going to give us 3 lectures. Today is a public talk. Tomorrow morning, or almost close to noon, there will be a high school talk. If you want to come, you're more than welcome. And then there will be another one at 2 o'clock, which will be across the hall, which will be more technical for graduate students and faculty. Now, the subject of the talk is actually very much in tune with current politics and the state of the world, which is randomness. Please, Avi.
Hi. Thank you. It's really a pleasure to be here. Everybody hears me in the back? Yeah, okay, very good. Okay, so the subject of my talk, it should be familiar to everybody, as Luis said. It ignites various connotations in the minds of different people. Randomness was used, in prehistory, I guess, even to break ties and for lotteries. People contemplated the role of chance in their lives, luck and stuff like that. Of course, it was studied more rigorously by all sorts of, by philosophers, by physicists, by statisticians, by mathematicians. What I want to tell you today is the point of view of my field, computational complexity theory, on randomness. It's at high level. I hope you'll understand everything or most of what I tell you. Of course, there's a wide background I expect in this audience. If something is looks totally unclear, stop and ask me. Okay, so let's see that works. All right, so here's the plan. First of all, I want to make sure we are on the same page. So the subject of the talk is the coin flip, the perfect randomness. If I flip a coin perfectly, that it lands heads 50% and tails 50%. So just to check, suppose I flip a coin 20 times. Which of these 2 sequences is more likely? Okay, good. Okay. So everybody agrees they are equally likely. They each have probability 1 in 2 to the power 20. This is what we call the perfect randomness or uniform probability on sequences, and we'll use it. We'll see how such sequences are used and what to do when we don't have them. So the first I'll talk about this amazing utility of randomness, and I'll give you lots of examples. And then we'll ask ourselves, what do we do? I mean, can we use them? Are they there? Or what do we do if we don't have them? And to tackle this, we'll talk about a notion called pseudorandomness, which is a study of deterministic structures, no randomness, which have similarity in behavior somehow to random ones. And I'll give you lots of examples and applications. And at the end, we'll see what can we do if we don't have perfect randomness and what we cannot do. So in this first part, this example, I'll give you just many types of uses of randomness, and you should have in the back of your mind, this will appear in every slide, is it real? I mean, can we actually have this application? Because for it we need random bits. So where are they coming from? That's just in the back of your mind. The first and extremely powerful demonstration of the power of randomness existed forever just for acquiring information, rough information, statistical information. So suppose we have an election, let's say in the US, and we have 3 or 350 million people voting, red or blue, and we want to roughly estimate who will win and by how much. And we know, I guess this is familiar to everybody, population surveys are frequently done. What you do is you just take a random sample. You select, let's say in this example, 2,000 people completely at random, so you need perfect randomness. But if they are chosen completely at random, and you just count the fraction of red voters in this sample, it will be extremely close to the actual fraction with very high probability. So for 2,000 people, you are assured that this estimate will be within 2% of what you want with very high probability, 99%. This is very powerful and is used all the time. In fact, it's even stronger because these numbers, the 2% accuracy and the 99% success probability, don't depend on the population size at all. If we did it in China, it would be the same. If every planet in the universe voted, it would also be the same. So it's very powerful, independent of population size. And in contrast, if you didn't have randomness, what would you do? I mean, you'll probably have to go one by one and ask everybody, maybe except for 2% of the population. So it's extremely powerful, and that's one of the best demonstrations. Now I'll give you some more demonstrations which are more recent and of a wide variety. So the next example is to algorithms. So computers were built and people started running algorithms, programs on to solve various problems. And here's the problem which actually seems difficult, will be familiar to some physicists in the audience. I give you this board, this region in space, and you see in the picture I tiled it with dominoes, and this is just one particular tiling of this region. There are many different ones. And it turns out that it's very interesting to estimate how many different tilings are there. This is called the dimer problem in physics. If you can count or approximate this number, then you understand something about the material which this models and various thermodynamic properties of this material. So it's very important to know how to estimate it, not just for this region, but for other regions in space. And if you have randomness, this number is huge, is humongous. So it's not easy just to count them, try all possibilities, but there's a very important and useful algorithm that was developed, which with randomness gives you a very fast program to estimate this number, as accurate as you want. Okay, so with randomness, this algorithm exists, and as far as we know, and this is, I want to stress that as far as we know, every deterministic algorithm that we know cannot do better than just enumerate the exponential number of possibilities. So there's a vast difference in efficiency between what you can do with randomness and without randomness. And this is just one example of many, many more. Just for the mathematicians in the audience, here's a list of some problems in different areas of mathematics, in number theory, in algebra, geometry, analysis. All of these problems have extremely fast probabilistic algorithms. We know them, people invented them. But as far as we know, for each one of them, if you try to solve them without randomness by a deterministic process, by a deterministic program, then it will take exponential time, which in layman terms means we'll never do it if the input is large enough. So efficiency is gained by the use of randomness with extremely high probability. So there is always error in probabilistic algorithms, but you can make it as small as you want. Here's another different type of application where actually randomness gives you the ability of doing something that you simply cannot, provably cannot do in a deterministic fashion. These are two problems in the area called distributed computing. This is a situation we have many, like the internet maybe, many computers interconnected. There's no global clock, so there's no synchrony. And in the first problem, you see these guys in this field have very nice names to their problems. One is the Dynamic philosopher's problem, the other is Byzantine agreement. The first one is really about resource allocation between the processor participating. The other one is about coordination between untrustworthy agents. And for both of them, there are theorems saying, one, there is a fast probabilistic program. Program here means distributed programs. These processors all are running their probabilistic algorithms. If they have randomness, then they can solve this problem very efficiently. On the other hand, for each of these problems, if the processors have no randomness, they are deterministic, then probably this may last forever. They will never achieve the task coordination or resource allocation. They may get stuck in a loop or in a blockout. So here, randomness really enables you to do something you cannot do otherwise for really real-world important problems. Okay, let me give you two more examples of where randomness is used. Actually, not just to do things, but actually to define correctly mathematical notions, important notions. The first example is the field of game theory. I'm sure many of you have seen description of competitive games. This is a particularly simple game where there are two players that each have one of two strategies, one aggressive and one, I guess, being cautious. And it sort of models, this is a game by Aumann, a Nobel Prize winner in economics. It sort of models two aggressive drivers towards each other in a narrow road, and each of them has an option either to go to the side, be cautious, or be macho and hope the other guy goes to the side. And the numbers in this matrix represent the payoff they get for each of, once you know their strategies, tells you how much each of them gets. I guess the minus three there is when they both are aggressive and will die, so maybe it should be minus infinity. At any rate, this is a description of a game, and there are many games, many important games that can represent it this way. A famous model or notion to capture what is a rational behavior for people competing in this sense, maybe there are companies competing or governments or any entities competing in such a game, what should be rational, what should they do, given all these numbers, which strategies they should choose. And famously, Nash invented the notion of Nash equilibrium, which means it's a collection of strategies for the players, so that knowing all the other strategies, the strategy you chose, you should not deviate from. You are not better off doing something else, knowing what the others are doing. This is the notion of stability, absolutely cornerstone in economics. But Nash didn't just get the Nobel Prize for defining this notion, he got it for proving a theorem. And the theorem says that every game, no matter how many players you have, no matter how many strategies each of them have, there is always a Nash equilibrium. Every game has such a rational behavior solution. The thing is that this needs an addition, that the solution is in mixed strategies, in randomized strategies. So this is true only if players are allowed to toss coins when they choose their strategies. For example, in this game, in fact, the only solution with these numbers is to be cautious with probability 3/4 and to be aggressive with probability 1/4. Okay, so you need randomness for this notion to be meaningful and to be applicable to every possible situation. If you disallow mixed strategies, if every player has to pick just one of the possibilities, then there are many games which have no what's called pure strategy. So here, randomness is essential for this definition. Another place where randomness is absolutely necessary is the field of cryptography, internet security, electronic commerce. You need randomness to pick your secret keys. Shannon already noted that a secret is just as good as the number, as the entropy in it, as the amount of randomness you invest. So if you choose it as a 9-digit number, then the probability that randomly, then the probability that anybody will guess it is 1 in a billion. But if you pick it, I don't know, it's a 9-digit number that is a phone number of one of your friends, even if you count Facebook friends and you don't, there aren't too many possibilities to go through. And then it's, okay, maybe I'll just stand here and look at my big screen and I'll see it better. Right, so secret needs randomness, and from then on, every possible use of cryptography, security on the internet, public key encryption, which is used for online shopping, digital signature, zero-knowledge proofs, many notions, and for each of them, randomness is key to the definition and, of course, to the application. Okay, and there are many more examples. Some of them are frivolous, maybe, but even here, it's not clear when you are going to a casino where is the randomness coming from. You better know something about it. So in all of them, it's key to understand where the random bits are coming from. So for this, we should ask this question: where are random bits coming from? Now I must say that I realized when coming here that I should have revised this slide, because I was going to ask, if you don't know anything, you don't know something, who do you ask? Today the answer is AI, but when I prepared this, some chatbot, but when I prepared this a few years ago, I was asking Google, which was the old answer to that. So I asked Google, where do you get random bits from? And Google gives you always a list of websites. And you look at them, and it's clear where you get random bits from. You buy them. So these are companies. There are actually 4 million answers. I don't know if all of them are companies, but basically there are companies which will sell you random bits. So random bits is an expensive resource. Some people are willing to pay. And then you want to know, how do they get their random bits? So you look at these websites, and some get it from the advertise, right? Radioactive decay, atmospheric noise, quantum phenomena. This particular one is actually used in casinos, or used to be used in casinos. Anyway, there are lots of sources they take random bits from. So are these good? Are these perfect? How do we understand that? So we need some way to define randomness. Again, because it was defined many times in many ways. And so for complexity theory, this will be, and for you to understand how we are thinking about this, this is the most important slide. So pay attention, and later you can relax. So I want to do one of 3 possible experiments, or to describe 3 possible experiments. And I need a volunteer from the audience. Avia, are you ready? It's there are no rewards and no penalties. It's just say what you think, right? I'm picking on her because she's Israeli, that's all. Okay, so here is you, here is me. I'm holding a coin on my finger, and I'm going to toss it, and it will land on the floor in 2 seconds or so. And while it leaves my finger, you have to guess whether it will be heads or tails. So in this experiment, what do you think is the chance you'll predict it correctly? Yeah, that's what I would say too. See, it's easy. Okay, good. So this was the first experiment. Now you are so good, I'm granting you a laptop. Maybe you have one already. It's on your lap, and we do the same thing. It's on your lap. I'm tossing the coin. You have to guess what it will be when it lands. What do you think are your chances? All right. Yeah, 1/2. Okay. Now we move to the third experiment. I don't only give you the laptop, I give you a bunch of video cameras, and they are all connected to a Cray supercomputer, and which is connected to your laptop, and all these cameras are trained on my finger. What do you think is the chance you'll predict it correctly? You have as many resources as you want, computational resources ready.
What, infinity?
Yeah, you have as much as you want. Yeah, I mean that's just the limit of the slide. You really have everything is yeah.
Almost zero.
Almost zero.
One.
No, what's the chance you'll guess it correctly?
I have. Okay.
Yeah, you have every. Yeah. So. Well, maybe, yeah, everybody's saying 1, and I would say 1 too. Because, with enough resources, you can figure out exactly the force I apply to the coin, the angular momentum, the humidity in the air, the distance to the floor, whatever you want. It's a process, once it leaves my finger, it's a deterministic process. And so you can guess correctly. So what's the point? What's the point about this story, about these 3 examples? The experiment, the tossing of a coin, which I said was the emblem of randomness, didn't change in all of these experiments. I was tossing the same coin. This was a random event. What changed is the observer, the computational power of the observer. So really, the meaning of this is that randomness is really in the computational power of the behavior. And this is a key point of view that we take when we think about randomness, that how predictable something is really depends on you, on the computational resources you have. And we'll see how we use it. But I want to point out this, unlike an objective definition, say the entropy of the event or something, this is an operative definition. It's subjective because different people with different entities with different computational power may view it as more random or less random. Okay, good. So now I want to start the second part of the talk, where I talk about pseudorandomness. And as I said, this is a study of deterministic objects that have something to do or look somewhat like random. So we imagine that we have some universe of objects. These objects can be various things, can be numbers or graphs or sequences or matrices or walks. You'll see examples. So this is a universe, and I call a property random-like, pseudo-random, typical, something like this, a property of the objects in this universe. I call it pseudo-random if it occupies most of the space. So there are several ways to think about it. That most elements have this property, that it's the hay in a haystack, that if I pick an element really at random from the universe, it will almost surely have this property. So any large property is, for me, pseudo-random. We'll see examples. In mathematics, the claim I want to make is that this is a basic phenomena, very useful notion in both math and computer science. In mathematics, usually people study questions whether some natural object, some element of this universe has a property. Many questions in math look like that. In computer science, rather than having some natural object, you just want a fast algorithm that will find you one element with this property. And this is like find objects that have random-like properties, which, if you look at the picture, it's like finding hay in a haystack, which looks, I want to claim that it can be a difficult problem, which looks ridiculous. So I want to explain why it may be difficult. And I have some examples that I hope will help. They are high level, and then we'll see more mathematical examples. But in general, even finding objects that abound everywhere can be difficult, sometimes because our view is very myopic. So if the haystack is the size of the real universe, and we are standing in some corner, maybe we see something else. And often we search for something only using what we know, techniques we have. So we don't see the real phenomena. Here are two examples. I ask you what's the color of this object. You'll say green, even though most of the mass is red. You just don't see it. And more interesting for some maybe astrophysicists here, this question of exoplanets has been around for decades or maybe centuries. All the stars we see are, of course, suns. And the question is whether these suns have planets. And this was not known up to about 25 or 30 years ago when techniques were developed. So somehow, you would argue, no planets, we don't see them, but actually almost all suns have planets. So once you develop some techniques for this, you can see them. Anyway, these are high-level examples. Let's see some examples of pseudorandom properties. One very important one is the error-correcting code. So we know, noise is everywhere, and in particular in communication, in the data storage. And so to be resilient to noise, we use error-correcting codes. We need good codes. What are good codes? Good that they can tolerate a lot of noise, a lot of errors. So these are good codes. And it turns out that good codes abound. Shannon proves, it's a very famous paper that started information theory and coding theory. He proves that if you pick a code that's random, it's a good code. The problem with this result is that this is not useful because, first of all, I want to stress, okay, it's a bound, then it's a pseudo-random property, but to find codes that are, somehow explicit, you can use them, you can encode them, you can decode them from errors, took 20 years or more after this discovery. So finding objects that abound is not easy. It's not always easy. It took a long time. Here's another example, a famous one. I assume you all recognize this number, right? So it has the following property. If you look, and people study this for billions of digits of pi, every digit, like 7, appears 1/10 of the time. Every pair of digits appears consecutively 1/100th of the time. Every triple, 1,000, and so on. So all these statistics happen just like in a random number. Suppose you demand, we call a number normal if it has this property, but not just base 10, also base 2, base 3, base 50, base 1,000,000. No matter what base you write it, it has the same, the desired statistics. Okay, so are there normal numbers? These are called normal numbers. Borel proves actually it's not difficult, that almost all real numbers, let's say in the interval between 0 and 1, are normal. So again, it's a pseudo-random property. It happens, almost every real number has this property. And to this day, we don't know how to answer basic questions in math, like is pi, this number, is it normal? It's just what we observe, square root 2, e, so on. We don't know. It's an open problem. Okay, so that's another pseudo-random property. So I gave you, two examples. Actually, they are interesting and important, but I want to say that actually the question about pseudo-randomness includes some of the most fundamental questions and most important problems, both in math and in computer science. So it's a point of view that is very general. Maybe I should ask graduate students in the audience How do you know when a problem is major? Anybody volunteers? Well, major, I say major problems, yeah.
My advisor tells me.
Yeah, exactly, that's what I thought you would say. But I mean, I say there's a more basic answer, money. Now, don't take me seriously. They do come with a $1 million prize on them, but yeah, I think there are better reasons to work on it. So these are the 7 millennium clay problems. They are famous. They were, you know, a team of mathematicians chose them as challenges for this 21st century as major problems. And one was taken, so if you want to gain $1 million using this way, you have 6 more. My point is that 2 of them are explicitly about pseudorandomness, and I'll explain this. The P versus NP, which is my favorite problem, and I'm not going to talk much about it here, and the Riemann hypothesis. In the first one, the pseudorandom property is being difficult to compute. So here the objects of the universe are functions. Almost every function is very difficult to compute. We know that. But we cannot lay our hand on a single difficult problem. This is a P versus NP question. So it's about pseudorandomness. I really want to talk about the Riemann hypothesis, which I'll explain in more detail in the next slide. Okay? So I want to explain why the Riemann hypothesis is a question about pseudorandomness. So maybe I should ask in this audience, there are many mathematicians, how many people can formulate the Riemann hypothesis? So you can just state, not solve, state the Riemann hypothesis. Raise your hand. Okay, so there are a few. So in 5 minutes, all of you will be able to state the Riemann hypothesis. And you will be able to explain it to your friends or your family members once you take this point of view. So here's the story of the drunkard's walk. So imagine this is a street, and in point 0, in the middle, there is a pub. And somebody walks into the pub, has a few beers, comes out, and starts walking up and down the street. Being random, being a drunkard here just means that, you know, it takes a step up the street or down the street with probability half every step. All right? And then you can simulate it. You can run a simulation of this process, and here are 10 simulations. And you stare at this. So this is the position of the walker after 100 time steps. If you stare at this, the most striking thing is despite the fact that the person walked 100 steps, it is about 10 steps away or 15 steps away, almost surely, from the pub. So somebody didn't get far. And in fact, it's an exercise you do in undergraduate probability that to prove that almost surely, if you walk n steps, you will stay almost surely within square root n distance from the pub, from the center. So it's a basic probabilistic statement. And when you stare it, by now, I hope I trained you to see if something happens almost surely, you call it pseudorandom. So almost every walk is, you know, homebound. So it's a pseudorandom property. And now we are asking whether a particular walk is homeward bound. So here's this property. So here's a particular walk. It's called the Möbius walk. And it's defined like this. First of all, for an integer, x, let's denote by p of x the number of prime divisor of this number x. So here's the list. And this, we define this Möbius walk, mu of x. So for every integer, we assign a bit. Well, it's 0 if this number has square divisors. You can ignore it. And it's 1 if the number of prime divisors is even, otherwise it's odd. So here's the list of the first 16 values of this p of x. And you stare at this. This is just a sequence of instructions for a walker to go up and down the street, or maybe stay in place sometime. Okay, so you can wonder about this particular deterministic sequence, whether it stays close to the origin or not. And now comes an important theorem, which is also not difficult if you can state a Riemann hypothesis. One is that this particular sequence stays within root n of 0 after n steps for every n, and the other is the Riemann hypothesis. So this is just an equivalent statement of the Riemann hypothesis in completely layman terms. Okay, maybe that's a way to solve it. I don't know. That's for the number theorists. Okay, so at least you can state the Riemann hypothesis. Okay, good. So now we've seen these examples. This point of view of assigning, I've given you properties that were defined structurally. Mainly, we either use these structural demands on numbers, on sequences, on walks, and so on, or we demand computational resource bounds on how long do you have to, look at them before you decide how random they are. Anyway, so I want to ask the question I asked in the abstract in the beginning of the talk. How do you cope? How do you use really have these applications I talked about in the beginning if you don't have randomness, or maybe if you have randomness that's not perfect? These encompass really major developments in computational complexity theory in the past 4 decades or so. So I want to consider 3 possible worlds. The first world is the world I was living in the first 15 minutes of the talk. This is a world where we have perfect randomness. We can do all these applications that I described. The second world is the world we feel we live in, I think. This is a world in which we have lots of phenomena that seem unpredictable. Maybe, sunspots, maybe radioactive behavior, decay, maybe stock market values, right? They all seem to have some unpredictability in them. Otherwise, we wouldn't be, losing money when we bet. So suppose we have, random sources that are not like perfect coins, but they are biased, for example. Like the weather tomorrow is more likely to be similar to today than very opposite. We have correlations, we have dependency. So you have some source with some entropy, who knows where it is, somewhat unpredictable, but certainly not perfect coin tosses. And it turns out that even with this type of sources, it turns out that all probabilistic algorithms I talked about, for all these mathematical and physics applications and many, many others, optimization and many others, can be executed despite the very, corrupted nature of this randomness. So this is a consequence of what we call extractor theory, or randomness extraction. This is really about purifying randomness. So we have efficient algorithms to take weak random sources, I'm not explaining how, to take weak random sources and somehow milk out the entropy of it in pure form. So it looks like perfect randomness, and then you can plug it in your favorite algorithms. Of course, using them as is will certainly fail. So that's a very beautiful and developed theory. Okay, so that's maybe the world we live in. By the way, this is used a lot on the sources I described in the Google search. People obtain randomness from internet traffic or radioactive decay or whatever other sources, and they apply extractors to them before they release them as random bits. But I want to consider maybe the most extreme situation when the world is deterministic. All the coins were tossed in the Big Bang, and now everything proceeds deterministically. Everything that happens maybe looks random to us, but is deterministic. So what can we do with probabilistic algorithms? Are they useful at all? So it turns out that yes, here we need an assumption. This assumption is something like the P versus NP question. In informal terms, you simply need some very hard function, some function that requires exponential time to compute. But let's make this assumption, because there are lots of problems for which we think that there are complexity. Under this assumption, it turns out that every efficient algorithm can be simulated, probabilistic efficient algorithm can be simulated deterministically. This is called the hardness versus randomness paradigm. You trade off computational hardness for pseudo-randomness. So again, the upshot of this theory is that every probabilistic algorithm that's used or will be invented and used that's efficient, that runs in a reasonable time, like the examples I showed, has a deterministic counterpart that's not much slower and has no error. All you need is one hard function. So that's, again, a second theory. And in both these theories, we use different notions of pseudo-randomness, and this is a very fundamental part of this development. Okay, I want to just end with an example of what a pseudo-randomness property that's actually used in such conversion, in this case, conversion of weak random sources to pure sources. So again, we have this ideal world with perfect random bits. We have reality, which, for example, I'm going to make the assumption that not only sunspots contain entropy, stock market values contain entropy, radioactive decay contains some entropy, even though they are weak, but let's say that they are also independent of each other. Suppose we have three such sources. I want to show you roughly how you can use them to make them perfect random bits, even though they are highly correlated and biased. And this requires a final pseudo-random property I want to talk about. This is pseudo-random tables. So here's the table, or matrix, 15 by 15, in which I draw at random, at every entry, a number between 1 and 15. Okay? And in this, if you do this experiment and you zoom in on any 5 by 5 rectangle, you'll see that you have many more than 5 values. Maybe you expect 5 squared. You cannot have 5 squared because it's bigger than 15. But you have many, many different numbers. No matter where you look, you'll find many more numbers than the size of this rectangle. A rectangle here, I mean just a bunch of rows and a bunch of columns. It doesn't have to be contiguous. So basically, theorem you can prove that in a random matrix, namely for almost all of them, now think of n by n, when you look at small windows, any small window will be very rich, will have many distinct entries. For people here who like numbers, think of this k, the window size is some power of n, and you want to have many more than k elements. You want k to some power between 1 and 2. Anyway, you want every small rectangle to be rich in many distinct entries. This happens to a random matrix, so it's a pseudo-random property, right? And now we want to build one. We want to find one. It happens, this property abounds, but we want to lay our hands on one such matrix. So one can construct such matrices deterministically? That's a non-trivial problem, and I want to tell you this story in the next slide. So you don't know where to get a table, and you think, well, what's the first table I ever saw? This is the addition table I saw in second grade, or first grade, I don't know. Is this a good matrix? If you look at small windows, are there small windows that are poor in entries? If you look at consecutive rows and columns or arithmetic progressions, you see that the diagonals will all be the same. So a k by k will have just about k entries as opposed to k to the 1.1 or 1.5. So this is really bad. And then you think, maybe what am I doing looking at what I learned in second grade? Maybe I should look at third grade. I learned the multiplication table. Maybe it looks more random. Sorry, the numbers are bigger than 15, but forget it. Anyway, is this good? You think about what do you think? Multiplication table is good or bad? Anybody ventures? Well, I mean, if you take geometric progressions of rows and columns, then you are back to basically addition, if you take logs. So it's also bad. So, and then the next thing you might think about is that John von Neumann warned us against trying such examples. He famously said, anyone who considers arithmetical methods for producing random digits is, of course, in a state of sin. But then you also remember that he ignores his own advice and actually did generate pseudorandom numbers using arithmetical means. He has famous pseudorandom generators that he used, so we ignore it. And it turns out that a very convenient and important theorem comes to our aid, which says the following. Even though each of these two tables is bad, if you look at them together, if you look at the numbers, for any window you look at the numbers in both of them, in the addition and the multiplication table, then together you'll get lots of different numbers. And this will be true anywhere you look. Oops. Okay, so that's, this is called the sum product theorem. It's important in number theory, in combinatorics, and in these applications to pseudorandomness. What do you do with this property? Turns out that this increase in the number of numbers in a window is sort of something that helps you increase entropy in your random source. The random source sort of selects just a few rows and a few columns, but using this boosting, you can increase the entropy. I will not explain it, but basically, you have your three sources. You add the first one, you add, and then you multiply. You just mix multiplication and addition, and you get higher entropy, and you can repeat it, and you get perfect random coins. So this is how some pseudorandom properties are used in order to generate perfect random bits. Okay, so what did we learn? Okay, I told you this main important slide. For us, randomness is in the eye of the computational power of the beholder. This is a very pragmatic, subjective definition. It's geared to applications, namely to probabilistic algorithms and using them when you don't have perfect randomness. So probabilistic algorithms survive even in worlds without much or without any randomness. The study of pseudorandomness goes beyond this application. It's useful for creating pseudorandom objects. I mentioned good for codes, for networks reliability, very communication networks which are robust, and many other applications. So, and also in mathematics. Okay, so that's my final slide, my commercial slide. For those who want to find more about this subject and many other topics in computational complexity theory, this book is available free on my website. And it's written, I think, in a friendly manner. So even if you are not in this field, you can learn a lot about what we do. Thank you.
Thank you very much for a wonderful lecture. Are there any questions? Well,
yeah.
Can you expand earlier?
Okay.
Earlier, you said that. Sorry, okay, it's weird with the mic. That fast probabilistic solutions have deterministic solutions when P is not equal to NP. Could you expand on that? Because earlier than that, you gave an example of a situation which exists now that has probabilistic solutions, but has been proven to not have deterministic solutions.
No, I never, so okay.
Maybe I'm misunderstanding.
Yeah, there are several clarifications needed for this. First of all, in all my examples, when I exhibited these fast probabilistic algorithms, I said there are no known deterministic solutions. I'm not talking about this distributed computational example. This is in a different model, and it's, it's not part of this story. But all this primality testing and volume estimation, and I don't know which, this domino counting, all these probabilistic algorithms can be de-randomized. You can remove the randomness from them, assuming that, I said P different and P in quotes, basically assuming that there is a problem that is exponentially hard to solve. There are many like this. You may know some of them. You know, there are famous NP-complete problems, for example, like, you know, traveling salesman to many optimization problems, satisfying Boolean formulas. Many people believe that factoring integers is exponentially hard. Anyway, there are lots of problems we believe are exponentially hard to compute. If you have one, if one exists, then you can remove randomness from every probabilistic algorithm and pay almost nothing. You know, you'll get as efficient as a randomized algorithm was. Is it clear? Yeah. Not how it's done, but what is.
I just thought there was a slide where it was proven that there weren't deterministic solutions.
This was the distributed computational. Yeah, so I talked about distributed computation when I mentioned this resource allocation and coordination problems. This is a different setting. This is a distributed system, asynchronous. You want to achieve something. It's a different model than just writing programs to your laptop. Right, so it's a different, maybe I should have clarified that. I'm talking about normal algorithms, computer programs you run. People run, you know, probabilistic algorithms all the time for lots of problems. For all of them, you don't need the randomness. If you have, you know, if P is different than NP in a moral sense, yeah. Yeah, it's sort of stunning, in fact. And it's an effective result. If you know what problem is hard, and we do know if a hard problem exists, then we know which problem to use because they are universal problems. You can use one of them to create a pseudo-random generator that will replace the random bits that were tossed in the algorithm. Yeah.
Here is a question.
Hi, thank you for the talk. I'm not a mathematician, so I don't know too much. So I hope you forgive me for asking perhaps a simple question. In that last thing which you showed where you have a set of numbers, it is all perfectly predictable, but the combination of them can give randomness? Is that how that is to be understood? Those two windows?
Not quite. It's the actual use of this property that I showed is somewhat sophisticated, but in a very high-level sense, you model your weak random source as selecting some, you know, okay. If you have perfect randomness, you select a random row and a random column, and you'll get a random number. But you cannot say your randomness is weak. It maybe selects only one of the first 5 out of the 15, or you know, few. That's basically a low entropy. When you have low entropy, you don't have all the possibilities. It's like what I talked about when I mentioned selecting your secret key as a phone number of your friend. That's very few possibilities. Okay? But if you get very few possibilities from several weak random sources, you can combine them by adding and multiplying them. This process turns out to increase the entropy combined from these sources. And you can do it several times until what you get at the end is really like you chose perfect coins.
Hi. So the first is just a comment. So when you asked me the third question, I thought you were asking what is the probability that I would guess the entire sequence correct.
Oh, no.
That's why I said 0.
No, that's okay. You got perfect marks on your answer.
And second, can you elaborate a bit on, like, is it possible to classify all the problems which you can deterministically solve, mimic the randomness, like at the table that you showed?
Okay, so as you notice, these are different properties. In the pseudo-randomness slides, for every application or you ask a different property from actually different structures, from tables, from works. Yeah, so it's a whole wide field. So there's no way to characterize pseudo-randomness in general, but one of the most useful ones in computer science applications, in particular to the randomized probabilistic algorithms under hardness assumptions, is simply saying that something is pseudorandom if you cannot, you, meaning somebody with bounded computational resources, cannot distinguish it from random. Okay? So in the olden times, in statistics, people were saying, oh, this sequence is random if, let's say, sequence of bits, if you don't see many consecutive ones, or you know, we were running various particular tests on it that would be also a property of a random sequence. But the most general we can think of is just I give you the sequence, and you tell me whether it came from a random source or you know, or somebody generated it deterministically. This kind of test, this kind of pseudo-randomness test, is the most effective one for computational purposes, and it's used all over the place in cryptography and in this de-randomization.
Jump here.
I have a question which is not directly relevant to your talk, but maybe it is relevant, just in case if you have a comment. So there is a field between mathematics and economics. It's called purification theorems.
How?
And
Verification?
Purification, yeah. The theory was originated many years ago in the work by Wald, Wolfowitz, and Dvoretsky, and so on. And they have a strange result. Basically, they have an example that purification doesn't hold, which means that randomized policies are better than non-randomized policy. However, under some assumptions in the standard analysis, the purification takes place. And then they translated these results from non-standard analysis to regular analysis. And for example, necessary condition when purification holds is the cardinality of the space is very large. Something like everything starts from 2 to the power continuum. So is anything that you can comment on randomness and the cardinality of the space?
So I don't know if I will answer your question, but I have 2 comments to make anyway. One is that the whole story I was talking about is concerned with discrete objects. Discrete objects, finite objects, large but discrete. So the whole theory applies to finite probability distributions. When you have continuous objects and uncountable and so on, it's a different game. The second is, maybe I didn't stress, but maybe your comment reminded me of, is that some things random bits can do, you cannot do deterministically. And this cryptography is maybe the best example. What can't you do deterministically? Just generate random bits. So we need, so it's not to solve a problem, but I just need, a 10-digit random sequence. Then, if I want to be random, I need to toss coins. So there are certainly things that you can do with random bits, if you have them, that you cannot do otherwise.
Okay, well, let's thank Avi for a great lecture. And in half an hour, there is a wonderful concert that I hope you can also join us for it. Thank you.